Greeting my data science friends. I'm making this short video to remind us about hypothesis testing and what that means and what it means in context of a p-value and a confidence interval. Okay, so let's pretend that this blue box represents some population of data that I really don't have access to. I'm not sure why I don't have access to it, but it's not completely there. So I don't have access to everything in that data set. So what a hypothesis test does is says, I'm going to hypothesize based on some parameter that I do have access to, some variable. What can I hypothesize? Well, let's hypothesize weight, for example. All right, so one of the things I can do is based off of hypothesis test, I'm going to hypothesize that this box is an ounce of gold. So I'm going to put inside this box an ounce of gold. I don't have access to that, but I can measure that against another box that I can actually put an ounce of gold. So now one of three things is going to happen. I let the scale go, and the first thing that could happen would be that this box weighs more than the box that I controlled with an ounce of gold. So in this case, I've proven without a shadow of a doubt that there is not an ounce of gold in this box. I have no idea what's in that box. There might be gold in that box, but I know it's not an ounce of gold, because if it were an ounce of gold, it wouldn't be heavier than my test box. The second thing, of course, that could happen was I get the situation of my ounce of gold is heavier than whatever's in that box. So now I have the situation where I've proven without a shadow of a doubt, no hesitation, that there is not an ounce of gold in this box. Whatever's in that box is lighter than an ounce of gold. There might be a gold in there for sure, but there's not an ounce of gold in there. If there were an ounce of gold in there, then I wouldn't get this result. So, in both of those first two cases, I've been able to disprove the hypothesis that there's an ounce of gold in my box. All right, the last scenario is this situation. I run my test and I get this result, where I get balancing. So now these two things give me no results. Now here's the key takeaway. If I were to say that whatever's in the blue box is equal to an ounce of gold because there's no difference, that would be a drastically bad error. Why? I know that there's an ounce of something in here in the blue box because this test of weight has shown there's an ounce of something in there, but I don't know what it is. It could be gold. It could also be an ounce of silver. It could be an ounce of butter. It could be an ounce of lead. It could be an ounce of sand. It could be an ounce of salt. I have no idea, right? So that's a hypothesis test. We can never prove something from a sample is equal to something we know. We can never prove it's equal. We can only ever prove that they're different. And that's the point that's important to remember about hypothesis testing. Unfortunately, a lot of people get this wrong. They see a p-value, they say, oh, I failed to reject, so therefore they're equal. Right? Okay. Let's talk about this confidence interval idea. Again, we're going to hypothesize that A equals B, and we're going to set out to try to disprove that A equals B. We can never prove that the blue box equals an ounce of gold. We're going to try to hypothesize that and then disprove it somehow. That's our goal, to disprove. If we fail to disprove it, we don't know anything about the blue box. Okay. But look what happens if they were equal and I subtracted B over the other side. Because A equals B, then the result is going to be 0. So if A and B are the same thing, the result is going to be 0. So in order to disprove that, I'm looking for this not to be 0. If A minus B equals 0, I don't know anything. I have no idea because I'm in the situation where the boxes are equal, right? And if the boxes are equal, then I don't know what I have. If the boxes are not equal, then this will not be equal to 0. So when I'm talking about a confidence interval, I want to make sure that inside my confidence interval, I get no 0. If it's less the low end than the high end, if 0 is trapped inside, I'm in this situation where A might equal B. And when A equals B, I have no idea what's going on. I haven't disproven anything. But if 0 is not within my confidence interval, then I know that I have this situation where they are different. If A was bigger than B, I would have this situation, but they're different. If A was smaller than B, I would have the other situation, like this. The key takeaway is I know that they're different. And so I'm really looking for confidence intervals where 0 is not inside or trapped inside the confidence interval. All right, let's take a look at an actual data set that I grabbed here. This is from, I randomly chose from the, let me pull this up here. I randomly chose 21 weights for men's football out of the Big Ten last week, randomly out of all the Big Ten teams. And then I randomly chose 21 of the weights from MAC teams out of the MAC for men's football. All right, so let's take a look. I'm going to scan this data into R. So B for Big Ten equals scan, and I put the data in for the Big Ten, and then M equals MAC. So that data for the MAC. I'm going to scan that in too. Those are the data sets. So I want to compare those two data sets. So one of the things I can do is make a box plot of Big Ten versus MAC weights at random. And I see over here, I get this. This is the Big Ten, and this is the second one, so this is the MAC. And you can see that it looks like the Big Ten is slightly bigger than the MAC. But the question is it statistically significant? Is this just due to randomness? The fact that the Big Ten, of these 21 randomly drawn characters or variables, is that just due to randomness, that it just happened to be bigger than this group in the MAC? That's the real question, and that's what a p-value tells us. What's the probability that this result was due to randomness? And so we want low randomness, right? If the probability due to randomness is really high, then we're not very confident in what we're doing. But if the probability due to randomness is really low, the results are really due to randomness are low, then we're excited about those results. All right, so let's take a look at the student's t-test. So it's t.test. And let's just look at B for Big Ten first. Let's look at that one. So I run the test, and when I run the test just for the Big Ten, the default in R is the one sample t-test, and it chooses a mean equal to 0, right? So if I read this, look at my 95% confidence interval. By the way, 95% is the default for the student t test in R. I can change this interval to using commands to a different interval if I want. But the 95% confidence interval is between 277.8 and 300.7 pounds. And I look at my p-value. This is 0, right? This is 0.15 zeros and then a 2. So this effectively is 0. So what it's saying is that the probability that this results is due to randomness compared to the mean average being 0 is 0, right? And if I look at my box plot, of that Big Ten group, like 0 is not anywhere near here. Possibility that this result was due to randomness is 0. My confidence interval in context shows me that 0 is not inside, and I'm confident that the true mean is somewhere between 277.8 and 300.7, the true mean of all Big Ten football players. I want to show you what happens if I tell the test not against the true mean being 0, but the true mean being, let's use the actual true mean, 289, or the mean of my sample. So now look what happens. The true mean is not equal to 289. So this is the problem. Look at my p-value. My p-value is really high. And look at my confidence interval. The thing that I'm testing against, 289 is inside my confidence interval between 277.8 and 300.7. So what that means is I think they're equal, right? But remember, in statistical testing, I'm not allowed to prove anything's equal. The true mean is not equal to 289. I have a really high p-value. And basically that means the probability that my results are due to randomness is really high. Versus, and I put value 289 inside my confidence interval, right? So is the actual mean equal to 289? So mu minus my results would be 0. 289 minus a proposed mu of 289. I would get 0 in there inside. It's the 289 is inside. So I don't know anything from this test. I can't tell anything. All right. Okay. So now let's look at Big Ten versus the MAC. So this is testing Big Ten versus the MAC. So now I have a 2 sample and see the true differences in the means. So between the two groups is equal to 0. And look at my confidence interval. It's between 8 and 40, the difference between the two. Okay? And I have a p-value that's really small, 0.004 or 0.4%. So in other words, the probability that I get an error due to randomness is only 0.4%. That's really small. And if I'm willing to accept that risk, then I would conclude that there is a difference between the average weight of a Big Ten football player and the average weight of a MAC football player. And then if I look at my 95% confidence interval, this is the difference between each group. It's between 8 and 40. That's my confidence. How confident am I about the differences in their weight? Well, it's somewhere between 8 pounds and 40 pounds. But the key is it's not 0, right? 0 isn't inside that group. Okay, our textbook author talks about the fact that we should always include a confidence interval in our report, and that's more important than the p-value. So make sure when you're making your reports in your data science field that you always put that confidence interval